Okay, in this video we're going to look at the second part of Chapter 6, and you want to be sure to watch this video before you attempt homework number 15. We are going to be looking at what we call the central limit theorem. Okay, so what I have here is a histogram, and this histogram is, I went on to and found a set of data with weights of people in kilograms. Okay, so you can see here, down here, change the color, you can see down here that the smallest person weighed somewhere around here 40 kilograms, and there was only one of them. And then we had a spike. There were 10 people up here around 65 to 70. Okay, and then our heaviest people were out here at 100, over 120, 130 or 40, something like that, kilograms. So is our distribution, would you call it normal? Well, sort of, but one thing I'm noticing here is we sort of have like a bump right here, and then we kind of have a second bump right here. Now, what do we think might account for these two bumps? Well, over here, when I tell you that these weights are in kilograms, that is of just randomly selected people. I think there were 80 people in the group that I took data from. And these are men and women. So one possibility is right here we get a little bump for women, okay? Because women on average tend to be a little bit lighter than men. So their average, their mean, their spike, their greatest population is going to be right in this area, somewhere around maybe 65 kilograms. Men would not be surprising to have a little higher average. So this is what we call almost like a bimodal distribution as opposed to a truly uniform distribution. Okay, so what does that mean in terms of what we can do with this data? Okay, so what I drew here was just a group of men and women. If you can kind of picture them, I know I'm not much of an artist, but you know, where did our histogram come from? Well, if we were to take this and create just a little bit of a frequency distribution, down here would be our weights in kilograms, and this would be our frequency, okay? And so, for example, maybe this person here weighs 80 kilograms, okay? And I did plug in all the weights, and it turned out that we had a mean weight of 78.9, so I'm just going to round that up to 79 kilograms with a standard deviation of way up here, 19.9. I'm going to round that to 20 kilograms. And I think part of the reason that we have such a high standard deviation is because our data is very spread out. This person here might weigh 80 kilograms, and let's say my mean is about here at 79 kilograms. So 80 will be about here. And so I would mark, you know, let's say maybe there's around 4 people, or maybe this person weighs 80 kilograms and this person weighs 80 kilograms. And so we have maybe around here is 80. And then we might have a very, very tiny person here, a lady here, who weighs maybe 40 kilograms. All right, so she's going to be way over here, around here, and there's not going to be very many of them. And I'm going to individually plot each person. This person's kind of heavy. This could be 100 kilograms out here. There's not going to be too many of those. A really big man, kind of an outlier, say he's 150 kilograms. Way, way out here, and so on. And I'm going to be plotting all these people. And the closer we get into the mean, the more people you're going to have. And we'll end up getting that sort of little spike for the women, and then maybe a little dip, and then another sort of spike for the men. And that's what it's going to look like when we plot each person's weight individually, each person's weight. So not only is that very time consuming, it can also be it leads us to a not normal distribution, which can be harder to work with. So what do we do? All right, imagine now, instead of plotting each person's weight individually, I take some groups. let's say I take equal groups of 6 people. So here's a group, 1, 2, 3, 4, 5, 6. Here's a group, here's another group of 6, 1, 2, 3, 4, 5, and 6. And I get all these different randomly selected groups of 6. 1, 2, 3, 4, 5, 6, so on, okay? And instead of calculating each person's weight, I find the average weight. What is the average weight for this group? So I would add up each person's weight. This guy weighs 79, and this guy weighs 85, and you guys know how to, this guy weighs 42, and so on. And you guys know how to find averages. You add everybody up. Well, what is the average going to equal? Well, maybe this whole group, they have some kind of small people, and the average is 75 kilograms, okay? And over here, this group is going to average maybe 80 kilograms. Okay. Down here, this averages looks like kind of a big group. They've got a really big guy. I would say maybe these guys average out to about 82 kilograms, and so on. And what do you already start to notice? For an entire group to have an average of 100 kilograms or 40 kilograms becomes less and less likely. Okay, so what if we plot this data? I'm going to do the same thing I did before. I'm going to create a table here. This is still going to be our frequency. Except down here now, instead of having the individual weights of people, I'm going to have the what we call the mean weight. Male coming up in kilograms, okay? And so what we're going to have here is, and these are going to be equal groups of groups 6. Okay, so 6 people in each group. My mean is still going to be 79. That's not going to change. The mean is not going to change. It's still going to change. But watch what starts to happen. Okay, because our men and women are all mixed up, we're not going to get that bimodal again. We're going to have some smaller groups, maybe somebody down here around 75, but there won't be as many of them. They're going to hover closer and closer and closer into that mean. And we'll have a few heavier groups. Maybe somebody in there's really heavy, and that group will be a little bit farther out here. But look what happens to our distribution. It becomes normal. Look at that. And that's your central limit theorem. When you start taking groups of data rather than individual data, your data, those means of that data becomes normal, which is very fascinating. Okay, cleaning that up and moving on to another slide now. What happens if we take an even bigger group? What if instead of this is our normal distribution of groups of 6, okay? What if, and I forgot to copy that part down. These are not weights anymore. These are the mean weights, okay, down here. Okay, let's say in another color here, instead of taking groups of 6, I'm going to take really big groups, say groups of, and I'm not use your imagination, really big groups. Let's say I take groups of 20 people, okay? 20 people in each group, 20 people. Another group of 20 people. Another group of 20 people, okay? And I find that average. I take those weights of all those 20 people, add them up, divide by 20. Guess what happens? Their average weight starts to get very close to 79. Maybe this average is up here is 79.5 kilograms. Okay, maybe this one over here is 80 kilograms. But because there's so many people in the group that even if you have some very, very tiny person or some very, very heavy person, it's not going to affect the ultimate outcome because you have so many people to offset it. You've got so many random people. So guess what happens to your curve? Your mean is still going to stay the same. Your mean is still 79, right? But what happens? You're moving in closer. Now here's 70, say 78 and 80. Okay, so you're actually going to have very few people out here, and what's happening now is your normal distribution curve is getting even more normal, is getting closer and closer into that mean value. So this blue normal distribution is groups of 20. So the bigger your groups, the more normal the curve becomes and the closer to the actual mean of the population you get to. All right? So what is the difference between this yellow curve and this blue curve? They share the exact same mean. But if you remember, standard deviation has to do with the spread. So while this standard deviation may be, the original standard deviation is very widespread. It was probably 20. So this one shrank, maybe this standard deviation is 10, right? But look at this one. This standard deviation is very tiny. This standard deviation is probably all the way down to 0.5 kilograms, and I'm just guessing. But the bigger your groups become, the smaller your standard deviation becomes. All right? The bigger your groups become, the smaller the standard deviation becomes. Your mean stays the same. And that is what the central limit theorem is. And it's just such a neat thing to use in the world. So going back to our original opening slide, what is the central limit theorem? And this is really in my own words, but as our sample size n, that's the size of those sample groups that you were taking. We took one of 6 and then we took another one of 20. As it gets larger and larger, the more normal our distribution becomes, and the means of the samples become closer to the true mean of the population, meaning that your curve will get narrower and narrower until it's getting closer and closer into this true mean of the population, the true mean. Okay? And what's so fascinating about the central limit theorem is that even if the original data is not normal, so you can look at all different kinds of normal, like weights, all kinds of data that is not normally distributed. So even if the original data is not normally distributed, the means of the samples will be normally distributed. And that is very applicable to life and one of the fundamental theorems in statistics. Okay? All right. So that was the lecture. What's going on? Now how do we apply this to problems? Okay. So here's a problem that was like the earlier that is really kind of review. So using our same weights of people where the mean was 79 kilograms and the standard deviation was 20 kilograms. It says, what is the probability of randomly selecting one person who is less than 90 kilograms? Okay, you should be pretty good at this by now. X in this case is weights of people, in kilograms. Okay, and these are individual people, this one person. So we're talking about one person. We are told that the mean is 79. We know the standard deviation is 20. So I'm going to plot 90 on my graph. It's probably somewhere about here, 90 kilograms. And I'm asked, what is the probability that someone is less than 90? So we're talking about all this space here, less than. All right, so this is all less than. Okay. All right, so just like we did in the earlier parts of the chapter, we have to find that z-score. We've got to standardize this 90, and the way we do that is we know that z equals x, which is 90, minus the mean, which is 79, divided by our standard deviation of 20. I punch all that into my calculator, and I get 0.55. Z equals 0.55, okay? And then the probability that z is less than or equal to 0.55, and actually I should have written this as equal to the probability that x is less than or equal to 90. That's going to equal, I go to my z table, which I'm not going to pull up now because we did that a lot in the previous video. It equals 0.7088, all right? So the answer to that question is the probability that of you randomly selecting one person who's less than 90 kilograms is about 71%. 71%. Okay, so that's review. All right, well, what happens when our group gets bigger? All right, let's say I ask the question, what is the probability of selecting a random group of 40 people and that they will have a mean weight less than 90 kilograms? Okay, so that changes my graph now. Now instead of being x being the individual weights of people, it is the mean weight. These are mean weights of groups of 40. Okay, groups of 40. Okay, but the rest, my mean is still the same. My mean is 79. Mean equals 79. But as you remember from the demonstration, when our groups get bigger, n is now 40. That's the size of our sample size. N equals 40. Our standard deviation is going to change. We're going to have to find a new standard deviation. Okay? Go with the formula. The formula for finding the new standard deviation is going to be the old standard deviation. Oops. Let me erase that. The old standard deviation, write the word old there, divided by the square root of n. So as you can see, as n gets bigger, because it's in the denominator, the whole number is going to get smaller. So watch what happens here. Our new standard deviation is going to equal the old standard deviation, which was 20. All right, that was the standard deviation of the original population, divided by the square root of 40. Okay, and if you now put that into your calculator, you will get 3.16. 3.16 kilograms. Wow, what a difference. Before it was 20, now it's all the way down to just 3 kilograms. So imagine where 90 is now. I'm still asked what is it, the probability that the mean weight is less than 90. So my 90 is still going to be to the right of my mean, but it's going to probably be a little farther out now, 90 kilograms, okay? And I'm still finding this probability that it is less than. So it's all this space here. First thing we need to do is find the z-score. So everything from here follows. We have one extra step, and that is it. And this is worth writing down, putting at the top of your paper. The only thing that changes when your sample size changes is you have to find a new standard deviation. Okay, so z is still going to equal the x, which is 90, minus this mean, which is 79, divided by the standard deviation, which is now 3.16. When you plug all that into your calculator, you're now going to get a z-score of 3.48. So our z-score went up by a lot. We're way out there, all right? So now the probability that our mean weight is less than or equal to 90 is equal to a z-score of less than 3.48. If you go to your z-table, because this is 3.5 standard deviations above the mean. We don't even look at standard deviations much above 3 because we're talking about most of the data, 0.999 something. I don't have my table with me, but I know it's very high. So we're now talking about 99.9%, almost 100% of people will have, 100% of the groups of 40 will have a mean weight of less than 90. All right. If I changed this to groups of, say, 100, if I change this group, if I said these were groups of 100, you know, it would get even more close, normally distributed. It would just, and the standard deviation would get even smaller, and so everything's getting in closer and closer and closer into that mean of 79. All right. So in conclusion, we just want to remember, and there's some questions on this in your homework, the central limit theorem applies if If your original data is normally distributed, then it works regardless of your sample size. If your original data is not normally distributed, like our weights, which was bimodal, the original data was bimodal, then your sample size should be over 30 in order to be able to use the central limit theorem. And when that happens, this is really all that you need to remember. It works the same way as the previous problems. It's just you have to find that new standard deviation, which is affected by the size of the sample. And that should be given to you in the question. All right, go ahead and attempt homework number 15 now. Good luck.